Welcome back to lecture number 11 on unit number 1, properties of fluid. This lecture will discuss the numerical on bulk modulus of elasticity. As far as bulk modulus of elasticity numericals are concerned, we have to memorize the expression of K, one in terms of volume, one in terms of density, and one in terms of uh, specific weight. As per the definition of bulk modulus of elasticity, it is compressive stress to volumetric strain. Compressive stress is change in pressure or increase in pressure. So K is equal to dP upon dV by V, but the negative sign is introduced in the equation to get the positive value of K. So K, its unit is Newton per meter square, like pressure. The same expression can be converted in terms of density. So minus dV by V can be converted into the d rho by rho, or same can be converted into a specific weight. So minus dV by V can be converted into d gamma by gamma. So this, as per the requirement, we can use these expressions. So the problem statement, first problem we will solve. So consider if the value of K of water is given, that is 2.07 10 to 6 kilonewton per meter cube. What is the pressure required to reduce its volume by 2%? So volume dV by V is given, that is change in volume to the original volume, that is 2%, but obviously it is negative. What will be the change in mass density? So initially dV by V is given, K is given. So in order to calculate pressure first, so we use the expression in terms of V. In this expression, K is given and dV by V is given. And dV by V is so minus minus plus. So the pressure required to reduce its volume by 2%, we can calculate. It is 414 bar or 41400 kilopascal. Now, in order to calculate the change in mass density, we have to use the expression in terms of mass density. So here K and dP value known to us. So we can calculate dP by rho, that is 0.020. This is a percentage change. Change in mass density, that is multiplied by rho. Rho as water rho value. Even if it is not given, we can assume it as 1000. So multiply by 1000 is 20 kg per meter. So this is the answer, final answer. So as per the requirement, so initially volume is given. That's why we can use the expression of K in terms of volume. And the change in mass density is asked. So in order to calculate the change in mass density, that is 0, we use the expression in terms of the second numerical. The pressure vessel has an internal volume of 0.1 meter cube at atmospheric pressure. It is desired to test the vessel at 3000 bar by pumping water into it. So the pressure vessel testing, generally the water is pumped, and the water is pumped at a very high pressure, that is 3000 bar, we can say. The estimated variation in change of empty volume of the container due to pressurization to 3000 bar is 0.6%. So in this case, because of the pressurization, so the pressure vessel is slightly expanded and its expansion is 0.6%. Calculate mass of water to be pumped into the vessel to attain the desired pressure level. Given that the bulk modulus of elasticity of water as 2000 megapascal. Now the volume is given, that is pressure vessel as an internal volume is 0.5 meter cube. Then the pressure desired is 3000 bar. K value of water is given. And the estimated variation, so that is change in volume to the original volume. So V2 by V1 divided by V1, that is given. So this is not at all a volumetric strain because this expansion is because of this high pressure. So because otherwise all the values of K expressions are given. So this expression is used to calculate V2 because V1 value is given, that is 0.5. So V2 is known to us because we have to calculate the mass of water to be pumped. So for that we require volume. So the final volume is after, due to expansion, the volume is increased, that is 0.0503 meter cube. Initial volume is this. So mass to be pumped to fill this much volume. So we can first calculate what should be the change in density. So K is equal to dP upon d rho by R because we have to calculate density part. So change in density to the original density is this much. So change in mass is 150. So this is dP. And mass density rho2, that is rho1 considering as 1000. So 1000 plus 150, that is 1150. Because rho2 by rho1, that is equal to dP. So rho2 is equal to dP plus rho1. Rho1 we can consider as atmospheric pressure. So this is a mass density after charging of or after pumping of 3000 bar water. Now we have to calculate the mass to be pumped. So M2 is equal to rho2 into V2. So that pumped mass of water to be pumped is 578.45 kg. So that that pressure can be reached. This is slightly a tricky example, but if you understand the statement properly, you could able to solve, because what is asked, that is mass of water to be pumped. So because of pumping of water at 3000 bar, there is expansion. So we have to consider the final conditions, that is V2. And in order to calculate mass, that is rho into V. So rho2, that is after pumping, and V2 is also the expanded volume. So mass of water to be pumped is 578.45 kg. So this is a slightly deceiving problem, because here the student can make a mistake that this can be considered as dV minus dV by V. So in that case, it is very difficult. And as mass is asked and density is to be determined, so we have used. So selection of expression is the key for solving problems, or we can minimize the time as well. So this particular technique is very important or useful while in the gate examination, because gate examination you have to solve the problem with minimum time. So that's why the same problem can be solved by using the expression of dP upon minus dV by V. First, we calculate the specific volume, change in specific volume. The inverse of that is change in density. Then we can solve. But here, if you use directly the formula of K in terms of d rho by rho, in terms of density, we can easily find out the value required answer with minimum time. Then the next numerical. So at a depth of 8 kilometers in ocean, the pressure is recorded as 81.8 megapascal. So 8 kilometers is a very deep, and then the pressure obviously, because of the water column, its pressure is also high. And assume this a specific weight of seawater is 10,050, and the average K value is 2.34 into 10⁹ Newton per meter square for the pressure range. And what will be the change in specific volume between that at the surface and that at a depth? what will be the specific volume at that depth, and what will be the specific weight. So these are the three questions asked. Now you can think about it. So at depth 8 kilometer, the value of dp is given 81.8, value of gamma is given, the average k value is given. So what should be the specific volume? So while in order to calculate the change in specific volume, you can use the expression in terms of volume. In order to calculate the specific weight, you can use the expression in terms of gamma. Two expressions you can use. So these are the values given with proper nomenclature. dp, gamma value is given. Rho1 given because it is in at the free surface. V1 is exactly the reciprocal of the same, and the k value is given. So first we use the expression of bulk modulus in terms of specific volume. So from this expression, we can calculate dV by V as well as d gamma by. So this ratio is constant. dV by V is obviously negative. So in order to calculate the change in specific volume, we use this expression. That is dV by V, that is equal to. So change in specific volume is multiplied by V1, that gives is minus 3.49 into 10 raised to minus 5 meter cube per kg. Obviously, dV is V2 by V1. And in order to calculate change in specific volume at that depth, so this is dV, V1 is known to us, V2 is equal to dV plus V1. So specific volume is positive, that is 9.42 raised to minus 4. So at free liquid surface, that is 9.76. So at that depth it is. Secondly, in order to calculate a specific weight, we use this expression. And from that gamma is, or change in specific weight is gamma 2 minus gamma 1, this much. So gamma 1 is known to us at free liquid surface. We can calculate the specific weight at that depth, is that is gamma 2 is this much. So this way we can solve the numericals. Mostly numericals can be asked for 4 to 6 marks sometimes. But again, you can rely on this particular expression, that is the value of k in terms of specific volume, in terms of density, and in terms of specific weight. If you memorize these expressions and with understanding of the statement, you can easily solve the numerical. That's it. At the end of this particular session, you should be able to apply the expressions or suitable expressions of bulk modulus for solving numerical. That's it from this lecture. Thank you very much.